Welcome to this explainer. Today, we're totally demystifying the electronics manufacturing process. We're going to take you on this incredible journey from a raw, unassuming piece of silicon all the way to that glowing, finished device you use every single day. Let's get right into it. So, let's kick things off with a pretty fundamental question just to reframe how we look at our everyday tech. How exactly does a literal rock pulled straight from the earth transform into that incredibly powerful smartphone sitting in your hand, or the monitor you're staring at right now? To answer that, we're following a zoom-in, zoom-out roadmap. We're going to look at 1, deconstructing electronics, 2, the silicon origin, 3, the IC skyscraper, 4, the protective suit, 5, the city grid, and finally 6, the final assembly. Section 1, deconstructing electronics, starting from the end product. You know, sometimes the absolute best way to figure out how something is made is to just tear it apart. Imagine we have a transparent PC or smartphone right in front of us. You zoom in, and the first thing you see is that big motherboard. Look a little closer, and you spot these individual black squares, right? Those are the integrated circuits, or ICs. But the real magic isn't the black box itself. If you zoom way, way down deep inside that IC, you'll find the tiny electronic brain doing all the heavy lifting, the microscopic die. Now, to cram massive computing power into that tiny space, without melting your device or killing your battery in 5 minutes, engineers have continuously shrunk these IC line widths. I mean, we've gone from 100 nanometers, shrinking down to 50, then 28, 14, and all the way to today's absolute cutting-edge 2-nanometer processes. It's just wild. Section 2, the silicon origin, birth of the raw wafer. Okay, so having zoomed in to the microscopic nanometer level, let's pull all the way back out to the physical starting line. Because before you can paint your masterpiece, you gotta prep the canvas. Before we can build any complex chips, we need to create the raw silicon canvas. This whole thing kicks off by pulling a massive silicon crystal ingot straight from a furnace, a super slow process that takes about a day and a half to 2 days. That giant cylinder is then sliced up into thin, circular wafers, rigorously polished and etched until the surface is absolutely flawless, and finally packed up and shipped to semiconductor fabs in specialized lots of 25. Section 3, the IC skyscraper, semiconductor manufacturing. So here's the crucial part. Once those perfectly polished, blank wafers show up at the fab, that's when the insanely complex manufacturing process kicks into gear. We are literally turning a flat mirror into a bustling, microscopic metropolis. First, let's make sure we're on the same page with our key unit, the die. You honestly don't need an engineering degree to grasp this. Just picture that big 12-inch silicon wafer as a massive sheet of freshly baked cookies. A single microscopic cookie cut out from that sheet, that's the die. And a single wafer can easily hold 800 to 1,000 of them. And this is where the skyscraper analogy fits perfectly. See, we can't just spread billions of components out flat. Instead, engineers build this incredibly intricate 3D high-rise of circuits. They dig deep trenches, stack metal layers for conductivity, and use oxide layers for insulation. And they use these things called contact holes, which act exactly like the staircases and plumbing in a high-rise, letting electrical signals travel vertically between the different floors. Section 4, the protective suit, IC packaging. All right, once our tiny 3D skyscraper is actually built onto the wafer, it is incredibly fragile. We obviously can't just toss it raw into a phone. It needs some serious protection for the physical demands of the real world. Think about it. We can't stick a 2-nanometer die directly onto a standard macroscopic circuit board. The size mismatch is just way too extreme. So we bring in a lead frame. It essentially acts as a massive adapter, scaling up those microscopic connections on the die to larger physical metal pins that a regular circuit board can actually interface with. This entire progressive sequence is what we call packaging. The fab sorts and tests the wafer, cuts out all those individual dies, uses literally microscopic wires to bond the die right to the lead frame, and finally molds the whole thing into a tough plastic or metal box. That protective suit completely seals the fragile physics of the chip inside a sturdy package you can safely handle. Section 5, the city grid, PCB manufacturing. Okay, so now we have our safely packaged IC buildings. Next, we need to lay down the city grid, where they're all going to live, draw their power, and communicate with each other. Enter the PCB, or printed circuit board. To connect all these different components efficiently, the PCB is built up in multiple layers using pressed copper foil. Precision machines come in and drill these tiny through holes into the boards, and then they plate the insides of those holes with copper. If you think about it, those plated holes are exactly like underground subway tunnels. They let electrical signals completely bypass the surface traffic and connect different neighborhoods of the board seamlessly. Now, let's clear up a critical industry distinction right here, because mixing up a bare PCB with a fully loaded PCBA is probably one of the most common rookie mistakes out there. A PCB is just the bare streets, that green board with only the copper lines. The PCBA is the populated city, that same board but fully assembled with all the chips, capacitors, and processors permanently soldered onto it. Section 6, the final assembly, PCBA, and putting it together. So how exactly do we bridge that gap from the bare PCB to the populated PCBA? This is our final zoom-out stage, where all these isolated parts finally come together into a real working system. The absolute hero of this stage is SMT, or surface mount technology. This is the bustling, high-speed construction phase. You have these automated robotic machines rapidly and with just insane precision, placing all of our packaged IC skyscrapers directly onto the surface of our empty city grid. The whole assembly basically flows exactly like this. First, the SMT line drops the surface components into place. Second, for the bulkier parts that need extra physical support, the DIP line inserts them right into those through holes we drilled earlier. Third, the board gets flashed with its firmware, basically giving it its software soul. And finally, EMS providers take this PCBA and put the whole shebang together with LCD screens, fans, and casings to create the final device. When you really step back and look at the sheer scale of everything we just covered, it is absolutely mind-blowing. Creating just that microscopic die alone is a massive 2 to 3 month journey that involves anywhere between 800 and 1,200 highly specialized manufacturing steps. Hundreds of global, perfectly synchronized processes happen seamlessly just to power the screen you're watching this explainer on right now. Thank you so much for coming along on this wild zoom-in, zoom-out journey with me. I really hope this leaves you incredibly curious about the highly orchestrated manufacturing universe that's humming away inside your pocket right now. So, out of this massive 1,200-step journey, which specific part totally fascinates you the most? Let that curiosity guide your next deep dive.